This is Stylianos. I'm a physics teacher with ATS in Align, and in this video we're going to solve the third part of the AP exam in electromagnetism from 2023. What we see on the diagram is a battery, a switch, two resistors connected in parallel, a capacitor, and one more capacitor on the right side, and he tells us that we have the two resistors, each one has a resistance R, and the capacitors have respectively capacitance C and 2C. And the first part is that we need to turn the switch to position A, the capacitors are both uncharged, and we need to write but do not solve a differential equation in order to determine the charge Q on the capacitor 1. I understand that we need to apply Kirchoff's law for current, voltage in the resistors and voltage in the capacitance, in the capacitor. So we're going to say that we're applying the loop law or Kirchoff's second law, which states that the summation of the EMF minus the summation of current multiplied by the resistance is equal to 0. When we say summation of EMF, we mean the EMF from the battery and the EMF of the capacitor 1, but the voltage of the capacitor 1 is opposing the polarity of the battery, so minus the voltage of the capacitance, minus current multiplied by the combination of resistor 1 and 2, so we need to go somewhere and say that the equivalent resistance for 1 and 2 is, because they are in parallel, 1 over R plus 1 over R to the power of -1. This is 2 over R to the power of -1, or R over 2. And we also need to remember that the capacitance is equal charge over voltage. This means that the voltage on the capacitor is equal charge, in reality this charge is variable, charge as a function of time, divided by the capacitance. So we get that EMF minus Q over C minus I times R over 2 is equal 0, but we need a differential equation, so we will also bring that the current is equal dQ over dt. So the final form of the equation will be E minus Q over C minus dQ over dt times R over 2, it is equal to 0. And this, I believe, will be our final answer. We move on now to part B, where we need to draw a graph, two graphs actually, one for the sigma, for the surface charge density on the capacitor 1, and the other one for the power through the resistors. Now let's examine what is actually happening on the circuit. We close the switch A, and this is where the capacitor will start charging. So the charge will be 0 at the very start, and it will increase until we get the maximum value. So the charge density, because it is charge over area, it is related to the charge. So the capacitor will have a 0 charge at the start, and the charge will increase until it reaches the maximum charge, and at that time the charge will remain constant. Now, for the same reasons, at the very start we have maximum current, and when the capacitor is fully charged, the current becomes 0. So since the power is current squared times R, the power depends in reality on the current, and the current starts from a maximum value until, on the steady state condition, the current becomes 0. So the current will decrease until it becomes 0, somehow like this. And we continue with part C, where it is stated that a long time later the switch is closed to position A, and the capacitor 1 has charge Q, and the capacitor the capacitor 2 is uncharged. And after that, we switch to position B. Now, when we switch to position B, what will happen is that since there is no more battery connection to the circuit, charge will flow from the capacitor 1 through the resistors to capacitor 2 until there is an equilibrium. So there will be a value of current until the equilibrium is reached and the current will be 0. And we need to state immediately after time 1, so when we close the switch to position B, what is the direction of the current, if it is to the right, to the left, or no current, in the switch. So again, from the diagram, since at the beginning the battery was connected like this, it means that positive charge gathers on the top side of the capacitor and it will start flowing to the right through the switch. So we say that the current is to the right, and we justify it by stating that there is positive charge on the top side of the top plate of the capacitor 1, and it will flow through the resistors to the second capacitor. So it will flow to the right on the switch. And we need to determine an expression for the total charge for the capacitor 2 after a long time. And we need to express our answer in terms of Q0, where Q0 is the charge on the capacitor 1. First, we need to say something about this Q0. The capacitor has an EMF, before we turned the switch on, there was an EMF that was the voltage of the capacitor 1. And from this, we bring that the C1 was equal Q1 over V1. So the C is equal Q0 over the EMF, that it is E. From this, we bring that the QO is equal C times E. I'm not 100% sure that we will use it, but this maybe will be useful later. And in order to determine the total charge on the capacitor 2, one thing that we can do is apply Kirchoff's law again. So the sigma EMF for the new circuit minus the sigma IR for the total resistance is equal to 0. Now, when we close the switch and after a long time, the only two sources of EMF are the capacitors. And because they have opposing polarity, we can say V1 minus V2. So V1 minus V2. And since there is no current, this term becomes 0. After a long time, there will be no current through the capacitors or through the resistors. So this is equal to 0. So V1 is equal to V2 for the two capacitors. Now, what we know is that the capacitance is equal Q over V. So the capacitance 1 is equal Q1 over V1. And from this, we bring that the V1 is equal Q1 over C1. So in a similar way, this left equation becomes Q1 over C1 equals Q2 over C2. But also, what we know is that there is the law of conservation of charge. So the charge on the capacitor 1 plus the charge on the capacitor 2 together, they will be equal to the initial charge of the capacitor 1, which was Q0. And since we need to find the charge on the capacitor 2, first we will solve for charge 1, which is QO minus Q1, and then we'll go and replace it in the left equation. So what we get is QO minus Q. Sorry, I made a mistake here. The Q1 was QO minus Q2. So QO minus Q2 over C1, which was C, is equal Q2 over C2, which is 2C. So C and C can cancel. And what remains is that 2QO minus 2Q2 is equal to Q2. So 3Q2 is equal to 2QO, and from this we bring the last result, our final answer, that the Q2 it will be equal to QO over 3, which is the final charge after a long time on the capacitor 2. And we continue to part 3, which is to derive an expression for the energy by resistors 1 and 2 immediately after time 1 until the new steady conditions have reached. So we need to find the energy of the system just before we turn the switch to position B and a long time later. Now, just before we turn the switch to position B, the only part that had charge and energy was the capacitor 1. And this means that we need to find the energy, the potential energy of the capacitor 1. And then, after a long time, there will be charge on capacitor 1 and charge on capacitor 2. So from the difference in the two energies, we will find what is the total energy dissipated. So we need to say that the potential energy before was, there are three formulas for the energy of the capacitor. Energy is equal 1 over 2 Q times V, and 1 over 2 CV squared, and 1 over 2 Q squared over C. Since we know that the capacitor 1 had the charge Q0, I think we're going to use the last law, which is 1 over 2 QO squared over the capacitance of the first capacitor, which was C. And the U after is equal the energy of the first capacitor and the energy of the second capacitor. Sorry for that. So 1 over 2 C1 squared divided by, Q1 squared divided by C1 plus 1 over 2 Q2 squared divided by C2. These Q1 and Q2 are the charges after we close the switch, a long time after we close the switch. So it will be 1 over 2. The Q1, I think that we didn't find it, but since the charge on the capacitor 2 is 2Q over 3, and the initial charge was QO, then the remaining from that is the charge of the capacitor 1, so QO over 3. So 1 over 2 QO over 3 to the power of 2 over the first capacitance, which is C, plus 1 over 2 2QO over 3 divided by the second capacitance, which is 2C. And I forgot the power of 2 here. So we get 1 over 2 QO squared over 9C plus 1 over 2 4QO squared over 9 times 2. So I'm keeping the 9 times 2C. The 2 and the 4 cancel. So we have 1 over 2 QO squared over 9C plus 2QO squared over 9C. It is 3 QO squared over 9C with the 3 and the 9 cancelling, and the remaining is 3 on the denominator. So 1 over 2 times QO squared over 3C. And in order to find the energy dissipated, we need to subtract these two values. So the delta U is 1 over 2 QO squared over 3C minus 1 over 2, sorry for that, 1 over 2 QO squared over C, and the 1 over 2 QO squared over C is common factor, so 1 over 3 minus 1, so 1 over 2 QO squared over C, and 1 over 3 minus 1, it is minus 2 over 3, so the final answer will be minus QO squared over 3C. And that's our final answer. And finally, on part D, we need to find the ratio of potential energies. However, something is happening to the capacitor too. He tells us that with the switch still closed to position B, this means that the voltage of that capacitor will stay the same. The parallel plates of the capacitor are moved so that the separation increases by a factor of 2. So we will have a change in the capacitance. The initial capacitance for the capacitor 2 was 2C, but it is given that the distance increases, and we remember that the capacitance is epsilon naught multiplied by area divided by the distance. So since the distance is increased by a factor of 2, it means that the capacitance from 2C, it will decrease by a factor of 2, so it will become C. And we need to find the ratio of potential energies. And in order to find the ratio of potential energies, a long time after we did this, a long time after we moved the plates, we need to figure out what is happening to the voltage. We know from the previous part, we had proved that the voltage of the first capacitor and the voltage of the second capacitor are equal, since they're still connected. We'll have the same relationship, that the voltage of the first capacitor is equal to the voltage of the second capacitor. So Q1 over C1, which is C, will be equal to Q2 over C2, but the new C2 is equal to C again. So from this we bring that the Q1 is equal to Q2. And since the two capacitors have the same charge and the same voltage, this means that the potential energy of the capacitor, which is 1 over 2 Q squared over C, we have same charge and same voltage, so U1 over U2, they will be the same, so their ratio will be equal to 1. I think this is our final answer. And we should briefly mention that since the capacitors are still connected, our relationship for the potential difference across the two capacitors still stands. So the voltage 1 and the voltage 2 for the two capacitors is the same. Also, we prove that the charge is the same. That's the reason why the ratio of potential energies is equal to 1. And finally, the part E, where we say that we bring the switch back again to position A, and we need to derive an expression for the current, and then exactly the same thing a long time after we turn the switch to A. So our capacitors are not fully charged. There is a charge that it is, we didn't find it, but there is a charge Q1 and there is a charge Q2 here, but these two capacitors are not fully charged. So when we close the switch back to position A, we don't care about how much charge is on the capacitor 2, but we need to figure out how much charge is on the capacitor 1, because since the capacitor is not fully charged, the capacitor will start charging again, and so there will be some current through resistors 1 and 2 until the capacitor is fully charged, and the current will be 0. So it is very easy to answer the second part. that we need to determine the current a long time after we switched the capacitor, the switch to position A. So the current after a long time will be 0. If there is a need for a justification when the capacitor is fully charged, there is no current. However, we need to find the charge immediately after we close the switch. So I think that we will try to apply the Kirchoff's law one more time. So sigma EMF minus sigma IR will be equal 0. Now the EMF is the EMF by the battery minus the EMF on the capacitor 1. And the current is the current that flows through the total resistance of R1 and R2. Now, we need to mention, we need to eliminate the E, and we need to mention what is the voltage of the capacitor 1. Now, we said that on the capacitor 1, the charge is Q1, and we don't know the value, but we knew that the Q1 and the Q2 together were charged 0, and we had also proved that the Q1 is equal to Q2. So the Q1 and the Q2 are equal. This means that the Q1 is equal to QO over 2. And we're going to use this in order to find what is the voltage of the capacitor. So the first capacitor has a capacitance C, which is Q1 over the voltage of the capacitor. This means that the voltage of the capacitor 1 is equal Q1 over C. So the voltage of the capacitor 1 is equal QO over 2 divided by C, so QO over 2C. So minus QO over 2C minus I times the resistance 1, 2, we had found it R over 2. All of this is equal to 0, and we need to eliminate the E of the capacitor. I think that we have proved something about the E. Now, when the capacitor will be fully charged, the capacitance will be Q over V. The maximum charge was QO, and the V was E. So we had that the E is equal QO over C. So we can replace this with QO over C. So what remains is Q over C minus Q over 2C. It is QO over 2C minus I R over 2 is equal 0. So QO over 2C equals I R over 2. The 2 and the 2 are eliminated, so the current is equal to QO over RC, which is our final answer. That's it. I hope you enjoyed it, and I hope that you learned something new today. Thanks for watching.